Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on reservoir engineering. And today's topic is about material balance calculation. And we have so many cases of material balance, but in today's specific video, we are going to talk about volumetric oil reservoir in undersaturated condition. So we are calculating the condition above the bubble point pressure. All right, so now this is the data that we have. Let's jump in directly into the data itself. So let's say we have unknown or something oil reservoir. All right, and then we know based on volumetric calculation, the geological computation, the in place, original oil in place is 293 mmstb. And then we also know the initial reservoir pressure to be 3,685 psi. Initial water saturation, 24%. And we also know that the bubble point pressure is 1500. So now our initial pressure is well above the bubble point. And then we also know based on laboratory measurement that the water formation volume factor is 1, and water compressibility we know, and also the rock compressibility, CF, we know. And then we also compile the production data and the pressure data, and this is the data that we have. We know the average pressure, and we also know the number of wells, the well stock, and we also know the oil formation volume factor as a function of pressure here. So we know the historical oil formation volume factor, and this is the cumulative oil production as well as the cumulative water production. And again, it's very important to consider or remember or to note that this is a volumetric reservoir. At least that's the first assumption. All right. And then we are asked to estimate the initial oil in place based on material balance calculation. All right. So we will later on compare the oil in place based on material balance, compare it with the volumetric calculation from geological computation. All right, so that's the case that we have, and let's jump into the strategy to analyze this situation. I already done the computation, but I will go through, or I will redo everything here. But let's talk a little bit about the strategy. All right, so now we need to first calculate the initial water and rock expansion term. Okay, this is volumetric reservoir, undersaturated reservoir, right? So we are not talking about mainly gas, no. So in that case, this value, all right, the initial water and rock expansion becomes significant, and that's why we need to calculate it instead of neglect it. All right, and long story short, based on the calculation, the material balance formula, you rearrange here and there, you get this EFW. All right, 1 plus M BOI, and then something here multiplied by delta pressure. But we know that we don't have any gas cap, so we can cross out the M here. And then we also know, or we need to calculate also the delta pressure. So it should be initial pressure minus the average reservoir pressure in time. And then we need to construct the material balance table like this. I will go through, I will redo everything here. And then using the value or results that we have, we just need to create plot like this. Okay, we will plot the F, the withdrawal against these expansion terms. And then from the slope of the correlation that we have, we will get the original oil in place based on material balance calculation. All right, and that's the thing. So now let's redo everything, okay? So I will erase everything here. Okay, so I have nothing on my plot. Okay, it's going to be very easy. So now let's first calculate the F. Again, F is the underground withdrawal. Simply, it's the production, but it's in underground, underground condition. That's why I use BBL, small BBL. It's talking about reservoir barrel instead of stock tank barrel, right? So it's underground withdrawal, whatever you take from the underground. That's why it's NP, but multiplied by formation volume factor to make the volume into the reservoir's perspective rather than stock tank perspective. And then also water production multiplied by BW. So we don't have gas in this case. Right, so this is very simple. Just, NP multiplied by BO at that time plus water production multiplied by BW at that time. And we can simply consider that the BW will be constant. Okay, so it's like this, and then you drag everything down there. Okay, so F underground withdrawal is very simple. Let's put it here. And then we also need to calculate the EO. EO here is or describes the expansion of oil and its originally dissolved gas. All right, so again, EO describes the expansion of oil and its originally dissolved gas. So EO mathematically is BO minus BOI. All right, because BO will be bigger than the BOI and EO will be positive. All right, so that's why it should be like this, BO minus BOI, and then you log this value, okay? And then just double click like this in Excel. Okay, so you get the value. All right, and then we need to calculate the EFW. E is expansion, all right? So EFW, just based on the index here, F means rock, W means water. So EFW represents the expansion. Again, E is talking about expansion of the initial water and the reduction in pore volume. Okay, so we will use this formula without M to calculate the EFW. All right, so, but before that, I need to compute the delta P first, right? Delta P is initial pressure minus the, the latest, the average pressure. So it should be this, put dollars there, and then minus the value itself. Yep. Okay, so from the initial condition down to the latest condition, we have, depleted 497 PSI. And then just compute the EFW using the formula. So it should be BOI. Maybe I can borrow value here. No, just use it here and then log multiplied by CW log multiplied by initial water saturation log, and then plus the CF. It's also a constant. And then close, and then open another parenthesis, a bigger one there. But now you divide this term with 1 minus initial water saturation. Lock, close, and close again. But not finished yet, multiplied by delta P. All right. You can change it from general, general format, but of course we prefer the scientific format. All right, and you can basically you can already go into the conclusion. So we have a plot here, or maybe we can read the step 3. Plot the underground withdrawal term against the expansion term. It's on the Cartesian scale. So in Excel, we just right click here, select data. I'm going to remove it first. Add no name first. Series X, horizontal axis, should be this. Oh, it's still blank. And then the y-axis should be the F here. All right. And of course, the last thing that we need to do is EO plus this. Boom. Okay, we got that. And then lastly, step 4, draw the base straight line through the points and determine the slope of the line and the volume of the active initial oil in place. Okay, so maybe I can squeeze it a little bit and then right click, add trend line, and we use linear and then also display equation on chart. And maybe you're also interested in, sorry, right click. Okay, and then, sorry, I just will redo the regression. Right click, add trend line, and then click this and this. All right, so now we have this one with R square approaching 1, which is very good. And then let's just color it with this, and then make it bigger. All right, so now you get the slope, which is the N. All right, this value, 290074. But don't forget, it's still in MSTB. So you get the active initial oil in place or the connected initial oil in place of 290,074 MSTB. So change it to MMSTB, just divide it by 1000. So you get that. So we have the active or connected original oil in place of 290. Okay, which is very close with the initial calculation, initial value that we have based on the geological calculation, volumetric geological calculation, which is 293 mmStB. All right, so this is my take. So my active oil in place is 290 mmStB. All right, and again, you don't need to choose between the geological computation, which is 293, or the material balance calculation, which is 290, because material balance will only focus on the production. So production comes from parts of reservoir that are connected to your wellbore. Okay, so it will not say anything about the parts of the reservoir that are inactive or that are disconnected, maybe with sealing fault or something, compartmentalization, something like that, that are disconnected to your wellbore. Okay, so you can differentiate between the results of material balance computation and geological computation. Okay, so now we get the final value, but we can also do something, another calculation or another diagnostics to ensure that it is actually a volumetric reservoir. Okay, and to do that, I'm going to make another plot. Okay, here. but it's F divided by the expansion term. It's like this, and it's very easy. It's F divided by this, the expansion term. And then do like this. Okay, it's like this. And then you just need to plot it against the cumulative oil production by time. All right. Okay, and then I just copy this. All right, maybe we can put it down there. I will just change the variables or the parameters. For the vertical axis, it will be this. And then for the horizontal axis, it will be this. All right. And then let's just change it to be, I'm going to copy this and then make it there. Okay, it's like that. And then it should be NP, okay, which is MSTB. Okay, it's like this. And then sorry. Okay, maybe I can make it smaller. Or, okay, and then change it. Yeah, just for looks. All right, so it's like this. Okay, of course, it's a diagnostic tool. Sometimes it's you need to do some, polishing works to make it, more reliable, okay, more make sense. So it's like this. But it's, I can say it's qualitative approach. So rather than using this as strictly, numerical or quantitative, I can just use this as a qualitative, diagnostics. And what I mean by that is I will draw a line and then make it something like this. I'm talking about horizontal line. And then maybe we can make it bolder, something like this. All right. And then because it's still early production, let's say we can neglect that. All right. Or maybe, yeah, I can make something here. Just, a note assigned to, to neglect this one for this diagnostics. And I'm emphasizing on this horizontal part. And qualitatively speaking, I can infer that it's horizontal rather than curved. By concluding that it's horizontal, I'm saying that it's a volumetric reservoir. So we don't have any aquifer support, aquifer impact on this reservoir. All right. Again, this is a case with volumetric oil reservoir. All right. And if you get this F divided by expansion term plotted against the cumulative oil production, and you get, the horizontal line like this, all right, then you have a volumetric reservoir. And the value here, the intersection between this line with the vertical axis will be the initial oil in place. So it's quite makes sense. It intersects close to or between 300 and 250. So, it's very close with what we have here as our initial oil in place, active initial oil in place, which is 290. All right, but again, it's a diagnostic approach. I can say that it's more qualitative rather than quantitative. So it's another, assurance that this is a volumetric reservoir rather than aquifer supported reservoir. All right, so I think that's all. I hope you enjoy this video. I hope this video and exercise of material balance is useful. Thank you so much for watching and see you again in the next Reservoir Engineering Analysis videos. Thank you.